Fourier transform and frequency domain analysis of LTS systems. Now we are going to move on to the last the Nyquist sampling rate and discuss in detail on sampling sinusoidal signals. And lastly, the concept of digital frequency. Now, the notion of ideal sampling was mentioned in part 1 to classify signals as discrete time signals versus continuous time signals, without much detail on how it works. Furthermore, continuous time signals are difficult to handle because digital computers can only handle samples or data. And the solution is called a continuous to discrete converter, C to D converter. And in practice, it is actually performed by the analog to digital converter, the A to D converter, okay, in practice. And the basic question to be asked is, how must we choose the sampling rate? So the important parameter here is actually the sampling rate in the C to D converter, so that the analog signal can be reconstructed from this sample through D to C, the discrete to continuous converter. And in practice, this is actually done by the digital to analog converter, the DAC converter. So let us consider this two signal. One is actually a continuous time signal, xt as a function of t, and another one is actually discrete time signal, x square bracket n as a function of n. And we know that t is actually a continuous variable, and n is actually an integer number, okay, at a discrete interval. And the continuous time signal can be converted to this discrete time signal through a process called sampling. So basically, you take the continuous time signal at a particular discrete interval here, and then that process is basically a time domain discretization kind of a process. Okay. So the basic question is actually that how do we decide on this sampling interval that we need to take? Okay. So that this discrete time signal is actually a good representation of this the original continuous time signal. And this sampling process is actually performed by what we call the uniform sampling, the uniform sampler. In this case, essentially we are taking this signal here, the xt, and multiplied by another signal, which is a periodic train of impulse function, or sometimes we call this an ideal sampling function, as shown here. Can be written as infinity to infinity function, and the inverse of full signal at infinity equal to n from minus infinity to infinity. You are evaluating the continuous time signal at that particular sampling instance, NTS here, and then you get a set of a delta function, and each of them is actually weighted by the sample value, which is actually shown in this diagram here. So therefore, every time when you multiply by the continuous time signal with a delta function, you are evaluating this signal at that particular instant. Likewise, you are taking the sample value here at this particular instant. Likewise, this is a sample value here at this particular instant, and this is a sample value here at this particular instant. So you end up with this set of delta function. Actually, set that. So if I substitute t by nts here, this will be nts or n over f of s, where f of s is my sampling frequency and ts is my sampling interval. So essentially, I'm just taking, to the sampling process, I'm taking the sample value at these sampling instances, and that actually converted into a variable. So it's delta n over f of s, where f of s is my sampling frequency with each of the weights actually given by the sample value. And SST here is actually a continuous time signal, because it's actually defined for all time interval, except that because the delta function only appears at a discrete time instances, so therefore it appears to be actually discrete in nature. And the same output of this uniform sampling can also be represented as a digital signal, x bracket n, which is by replacing this t here by nts. So if I substitute t by nts here, this will be nts or n over f of s, where f of s is my sampling frequency and ts is my sampling interval. So if you process, I'm taking the sample value to a n. Okay, as in discrete in nature, because here, okay, of interval. Okay, uniform sampling operation, and this can be simply achieved by multiplying it to the continuous time signal xt square bracket n here, the sampling. It is clear that if you at n equal to the t equal to nts or n over f of s, and obviously it is clear that if you change the sampling interval or you change the sampling rate, and you're going to obtain a different number of samples actually per second. So here we show the original continuous time signal with actually half of TS. And then in this case, one is you take one sample and be even higher. Then is actually that when you take can accurately. And this cost less difficult to handle because digital computers can only handle samples of data. And the process of converting continuous time signal to discrete time signal is called the sampling or the sampling process. A system which perform the sampling operation is called continuous to discrete the converter, C to D converter. And how must we choose a sampling rate in the C to D so that the analog signal can be reconstructed from the sample and low pass by the impulse train signal. Sometimes we call this is ideal. In this lecture, we are going to answer the question on how must we choose the sampling rate by developing low-pass sampling theorem and also introduce the concept of Nyquist sampling rate. Let us consider a band-limited signal xt with a Fourier transform capital S of f. So this is xt in the time domain with a Fourier transform with its amplitude spectrum given and shown here from minus fm to fm, where fm is the bandwidth of the signal. And we say that the signal is called band limited if the bandwidth of that signal is actually a finite quantity. So fm here is actually less than infinity, is a finite quantity. So mathematically, if we denote fm as the bandwidth of the signal, then the signal is called band limited if fm is actually less than infinity. So it's actually a finite number. In other words, a signal is called band limited if the amplitude spectrum here has a zero value for the frequency actually larger than the fm. So what it means actually that this is amplitude spectrum here has a zero value for the frequency actually larger than the fm. So what it means actually that this is anything outside here will be zero. So therefore, this amplitude spectrum here behave like a low pass spectrum, and therefore the term called low pass sampling theorem. So we're dealing with this kind of baseband signal. And it's important to note that the band limited signal is referring to the signal itself as its intrinsic characteristics. It has nothing to do with the filters we discussed earlier at all. So this is the intrinsic characteristic of this time domain signal. Now, example of band limited signals are, let's say number one is actually sinusoidal signal of, in this case is 3 cosine 10 pi t. In this case, we know that the frequency here is actually 5 hertz if you represent it as a 2 pi ft. And so therefore, there's only one frequency component, which is a finite quantity. Another signal which you are familiar with is actually the audio signals. And typically the audio signals are band limited with frequency a bandwidth of 20 kilohertz. So the audio signal with all this musical instrument and all that has a bandwidth of 20 kilohertz. And a bandwidth of signal which is not finite, say FM is actually infinity, is not finite, then the signal is called non-band limited. Okay. Example of non-band limited signal is a rectangular pulse of duration tau and amplitude A, discussed in example number 3. So recall that this rectangular pulse from minus tau over 2 to tau over 2. So the duration is actually tau, amplitude A here. Earlier on, we showed that this one has a Fourier transform, which is given by A tau sin of F tau. So it's a sinc function. And we know that if you plot the amplitude spectrum of the sinc function here, it has a frequency content behaving this way. So this is actually extend to infinity, and the amplitude at this point here is A tau. Okay, and the first zero crossing point is 1 over tau, and the second zero crossing point is 2 over tau. This is minus 1 over tau, and minus 2 over tau, and so on. Okay, so you can see that the sinc function here has infinite number of frequencies, so therefore it is a non-band limited signal. So the question is, how can we convert a non-band limited signal to become a band limited signal? Of course, one effective way is actually to pass this non-band limited signal, in this case is a rectangular pulse, through a low pass filter. So if I choose my low pass filter to have a cutoff frequency at 2 over tau here, then you find that this part of the spectrum will be actually rejected by the low pass filter. So you end up with only this band limited kind of spectrum, okay, with a bandwidth given by 2 over tau. Right, so this is a effective way by passing it through a low pass filter. And in example 1, when we discussed the frequency domain analysis of LTI system, we did look at the pulse response of an ideal low pass filter, and we have shown that actually when you pass the rectangular pulse through a low pass filter, at the output of the low pass filter is actually you cannot get exactly the rectangular pulse. It's actually a distorted version of the rectangular pulse. And if you choose the bandwidth big enough, the output of the low pass filter actually resemble the ideal rectangular pulse. Okay, but it has certain kind of ringing kind of edges before and after that the pulse duration. But at least it has the same kind of the pulse duration, which is same as the original rectangular pulse. Now, let us now develop the low pass sampling theorem, and here we're going to use 2 fundamental properties. Number 1 is actually that we're going to use the property number 11 of Fourier transform. When you multiply 2 time domain signal, it becomes a convolution in the frequency domain. Okay, so multiplication in the time domain becomes a convolution in the frequency domain. So this is actually property number 11 of the Fourier transform. The second property that we're going to use here is actually that earlier on we also showed that when we have an ideal sampling function, delta TS here. This delta TS is comprising actually a set of delta function when n from minus infinity to infinity, delta t minus n ts, where ts is usually the sampling interval. And then this ideal sampling function here will have Fourier transform given by, again, consisting a set of delta function in the frequency domain. Each of them is actually weighted by a coefficient 1 over ts. Again, consisting ideal when n from minus infinity to infinity, delta t minus n ts, where ts is usually the sampling interval. And then this ideal sampling function here will have Fourier transform given by, again, consisting a set of delta function in the frequency domain. Each of them is actually weighted by a coefficient 1 over ts. So applying this to property that the sampled version of the time domain signal is replacing t by nts. So in this case, I'm going to multiply this xt with the ideal sampling function. And so this xt here has a Fourier transform given by capital XF, and this one has a Fourier transform given by 1 over ts summation n from minus infinity to infinity, delta f minus n over ts, or nfs, right? And this is a constant which you can move it outside, so I can actually perform the convolution first and then sum out, okay? So in this case, I'm actually performing the convolution between S of f with a delta function, and you know that the result will be shifting this spectrum here to the position of that delta function, okay? Which is replacing f by minus f minus nfs or n over ts. So you end up with this very neat equation. This spectrum here to the position of to infinity, delta f minus n over ts, or nfs, right? And this is facing again function delta property Fourier transform. The second property that we're going to use here is actually that earlier on we also showed that when we have an ideal sampling function delta Ts here, this delta Ts is comprising actually a set of delta function when n from minus infinity to infinity, delta t minus n Ts, where Ts is actually the sampling interval. And then this ideal sampling function here will have Fourier transform given by, again, consisting a set of delta function in the frequency domain. Each of them is actually weighted by a coefficient 1 over Ts. So applying this to property that the sampled version of the time domain signal is replacing t by nt. Ts. So in this case, I'm going to multiply this xt with the ideal sampling function. And so this xt here has a Fourier transform given by capital XF, and this one has a Fourier transform given by 1 over Ts summation n from minus infinity to infinity delta f minus n over Ts, or nfs. All right, and this is a constant which you can move it outside, so I can actually perform the convolution first and then sum out. Okay, so in this case, I'm actually performing the convolution between S of f with a delta function, and you know that the result will be shifting this spectrum here to the position of the delta function. Okay, which is replacing f by minus f minus n fs or n over Ts. So you end up with this very neat equation that the Fourier transform of the sample signal is actually consisting a set of f, t, x, s, f, and so on. Okay, as a sampling frequency. I grant the original spectrum of the analog signal, of the baseband signal. And this is actually the Fourier transform of the ideal sampling function, comprising a set of delta function. Each of them is actually weighted by a constant 1 over Ts. So here, you're going to convolve this with this, okay? This is a convolution. And here we're going to consider three cases. The first case is Fs is greater than 2Fm. Second case is Fs exactly equal to 2Fm. And the third case is sampling frequency is actually less than 2Fm. All right. And you know that when you convolve this spectrum here with a set of delta function, you are shifting this spectrum here to the position of the delta function. All right. So you end up with shifting the spectrum here to the position of the delta function. And you end up with the resulting spectra after the convolution, position of the delta function. Shifting the spectrum here to the position of the delta function. And you end up with the resulting spectra after the convolution, which is given by this equation here. And graphically, this is what it means. Okay, so you have the And then you have a shifted version at the position of Fs, which is this guy here. 1 over Ts is Fs, right? And then you have likewise, you have 1 at 2Fs and 1 at minus Fs and minus 2Fs and so on and so forth. So this actually extend to infinity. Okay, so many copies. So this is for the first case. For the second case, where sampling frequency is exact, okay, Fs is actually 4 Fs minus Fm with this term which are not in the original. So therefore, in order to really preserve the original analog signal, you must actually sample at least 2 times of this or greater than this. Okay, because for these 2 cases, I can actually recover the original signal, the frequency content, by passing this through a low pass filter. So the low pass filter will remove the rest of the frequency component and actually recover back the original spectrum. Now for this case, there's no way I can recover the original spectrum because of this frequency overlapping. So the interpretation of the G5 result is that before sampling, S of F is the Fourier transform of the original signal, which is also called the baseband spectrum. And after sampling, the Fourier transform of the sample signal produces infinite copies of the baseband spectrum in the frequency domain, with each copy centered on the integer multiple of the sampling frequency, including the origin, besides the scaling factor of 1 over Ts being multiplied on each copy. Okay. So therefore, the low pass sampling theorem states that we must actually sample at the rate at least 2 times of the highest frequency content of the analog signal. So we must sample at least equal to 2 FM or greater than 2 FM, so that the spectrum here will not be overlapping, right? And the highest frequency content is actually the FM here. So therefore, the condition is that the sampling frequency must be greater or equal to 2 FM. Or you can rearrange this, means FM divided by the sampling frequency must be less than or equal to 0.5, in order to ensure that the sampled version, therefore, FM at least 2 times of the highest frequency content of the analog signal. So we must sample at least equal to 2 FM or greater than 2 FM, so that the spectrum here will not be overlapping, right? And the highest frequency content is actually the FM here. So therefore, the condition is that the sampling frequency must be greater or equal to 2 FM. Or you can rearrange this, means FM divided by the sampling frequency must be less than or equal to 0.5, in order to ensure that the sampled version, the sequence of sample, the sampled version of the original signal can preserve the frequency content. Okay. And since we are dealing with the baseband spectrum here, because this baseband spectrum has actually 2 sided, so is it imply that actually this Fm over F of S here must actually satisfy this condition, that this is actually in the range of minus 0.5 0.5. Okay, greater or equal to minus 0.5 to less than or equal to 0.5. Now, the Nyquist sampling rate is simply state that is equal to 2 times of the maximum frequency. Right. So the Nyquist sampling rate will be simply just a 2 times of FM, all right, which is actually corresponding to this case. And sometimes we call that as a critical sampling, right? So in other words, you must actually sample at least 2 times. If you sample below that, you're going to end up with this situation, okay, which is not good because the original content actually get distorted. So the Nyquist sampling rate is actually simply equal to 2 times of FM. So let us use 2 examples to illustrate this. In this example 1 here, we're going to consider 2 set of sinusoidal signal. One is simply 10 cosine 426 pi t. In this case, my frequency of the signal is actually 213 hertz. This is a single tone, okay? So the Nyquist sampling rate will be 2 times of that, will be 426. Second example, I have a sum of 2 sinusoid, right? XT is actually comprising 2 sinusoidal signal. One at 426 pi t with a phase angle, and the other one is a 1200 pi t with a phase angle 20 degree. So in this case, my frequency here, F1 is actually 213. And so therefore the Nyquist sampling rate will be 2 times of that, will be 1.2K. So in summary, when we talk about oversampling, it implies that the sampling rate is actually greater than the Nyquist sampling rate. Okay, so you sample at a rate higher than the Nyquist sampling rate, we call this as oversampling. And we're going to result in more samples being generated without aliasing. For the critical sampling case, where you sample exactly at the sampling rate, the Nyquist rate, then this is a required minimum sampling in order to ensure that there's no aliasing. For the third case, when you sample at less than the Nyquist rate, then we're going to result in less sample being generated, but with aliasing happening, okay, which is actually not good because in this case, you will not be able to recover the original baseband signal. So let us provide a summary on the key concepts that we cover in this lecture, summary number 2. So in this lecture, we we define the signal, which is actually band limited if the bandwidth is actually finite. So FM here is actually less than infinity, okay? And when that is true, then we call this signal as a band limited signal. And the Fourier transform of the sample signal have developed the low-pass sampling theorem and the concept of Nyquist sampling rate in the previous lecture. In this lecture, we will consider sinusoidal signals undergoing the sampling process to illustrate the concept of sampling theorem in greater detail. So let us consider an analog signal, xt, which is a sinusoid given as a cosine omega naught t plus the phase angle, which is undergoing a sampling process to generate its discrete time version, xn. And in general, we wish that the xn can still keep the frequency content of xt after the sampling. And here we're going to introduce the notation using the subscript a to denote the analog signal, and d, the subscript d, to denote the digital signal or the discrete time signal. So fa is then the analog frequency of xt, which is also equal to f naught, and fd is the normalized frequency or digital frequency of the discrete time signal xn, and fs is the sampling frequency. So the discrete time signal can be obtained by sampling the analog signal. In this case, we can replace t by nts, where ts is the sampling interval. So in the previous equation here, I'm going to replace t here by nts. So in this case, I have 2 pi f naught nts plus a phase angle, and we know that the sampling interval is the inverse of the sampling frequency. So I can substitute ts in terms of 1 over fs, and then I can group this f naught here is my analog frequency fa. So I can group fa divided by fs together, and we're going to define this equal to fd. So fd is the digital frequency or normalized frequency given as a fa divided by fs, and the unit is in cycles per sample, because fa is cycles per second, and fs is number of samples per second. So the unit of fd is cycles per sample. And frequency and omega, they are related by a factor of 2 pi here, so we can also define omega d here is actually 2 pi fd. And in this case, omega d has a unit in terms of radians per sample. So therefore, my discrete time signal of the time per sample, and here, so the substitute sampling f naught by nts. It's a phase angle, and we know that the sampling interval is the inverse of the sampling frequency. So I can substitute ts in terms of 1 over fs, and then I can group this f naught here is my analog frequency fa. So I can group fa divided by fs together, and we're going to define this equal to fd. So fd is the digital frequency or normalized frequency given as a fa divided by fs, and the unit is in cycles per sample, because fa is cycles per second, and fs is number of samples per second. So the unit of fd is cycles per sample. And frequency and omega, they are related by a factor of 2 pi here, so we can also define omega d here is actually 2 pi fd. And in this case, omega d has a unit in terms of radians per sample. So a cosine all the way to minus infinity. And it is very important to note that xn is not necessarily a periodic signal. We know that the sinusoidal signal in the continuous time case is always periodic, but once you sample the signal, the resulting signal xn here is not necessarily a periodic signal. It all depends on the value of fa and fs. Okay, so it depends on this quantity here. So let us consider this periodicity of the sample signal in greater detail. And if the discrete time signal is actually periodic with a period n naught here, which is samples per cycle, then if I replace xn by n plus xn plus n naught here, so I end up with a cosine 2 pi fd n plus n naught plus a phase angle, and I cross multiply, I end up with a 2 pi fd n plus 2 pi fd n naught plus a phase angle. And if xn is periodic, that means this is also equal to the xn here, right? So in order for it to be the same, then this fd n naught here must be equal to an integer number. So if this must be equal to the integer number, so you end up with 2 pi fdn, right? The xn plus n naught here. So I end up with a cosine 2 pi fd n plus n naught plus a phase angle, and I cross multiply, I end up with 2 pi fdn plus 2 pi fd n naught plus a phase angle. And if xn is periodic, that means this is also equal to the xn here, all right? So in order for it to be the same, then this fd n naught here must be equal to an integer number. So if this must be equal to an integer number, so you end up with 2 pi fdn plus n pi. This will be n pi and plus a phase angle, and this will be actually back to the original signal. So the condition for periodicity of the analog signal, sinusoidal signal after sampling, will be that the 2 pi fd n naught here must be equal to n 2 pi, where n is an integer number. And I can remove the 2 pi here, which implies that fd, in this case, the digital frequency or the normalized frequency, which is defined as fa divided by fs, must be a ratio of 2 integer, and therefore it must be a rational number. Okay, so only when the ratio between the analog frequency and the sampling frequency is a rational number, then the result counting sample sinusoids will be periodic. So let us use example number 2 to compare the sampling rate or different sampling rate for a particular sinusoid signal given as cosine 2 pi ft. In this case, my frequency here, my fa here is equal to 60 hertz. All right, and here the two sampling rate will be at 240 and 1000 sample per second. The corresponding sampling interval will be 1 over 240 will be 4.167 millisecond. For the second case, it will be 1 over 1000, which will be 1 millisecond. And the analog frequency is 60 hertz or 2 pi times 60. So after sampling at 240 or 1000, you end up with the omega d for the 240 will be 2 pi f divided by the sampling frequency. So this is my digital frequency, fd. For the 1K sampling rate, you end up with 2 pi multiplied by 0.06. So the fd here is 0.06. And the unit of omega d will be radian per sample. And I can then write my sinusoidal with 0.06. And the unit of omega d will be radian per sample. And I can then write my sinusoidal sequences as x240. This denote that the sampling rate is 240, will be cosine 0.5 pi d, pi n. and x1000 will be cosine 0.12 pi n. And it turns out that we can actually reconstruct the original signal from this either sequence, okay, because of the fact that the original frequency is 60 hertz, my analog frequency is actually 60 hertz. So in fact, the sampling rate must be at least 2 times of FA. That's what we learned from the low pass sampling theorem. So it must be at least 120 hertz. So for this case, you are sampling at 240 and 1000. So the sampling rate that we have for this case, 240 is actually much greater than 120. Okay, so they're actually above the Nyquist sampling rate, right? And 1000 is much greater than 120. So therefore, these two sequences actually, we can actually recover the original signal from here. So the question to be asked here is actually that are there other continuous time sinusoids that when sample result actually in the same sequence values as x240 and x1000? And so are there other continuous time sinusoids that when sample results in the same sequence value as x240 and x1000, right? And it turns out that yes, there are many other set of sinusoidal signal, as long as the frequencies are f analog plus or minus the sampling frequency, or analog frequency plus or minus 2 times of fs, and so on and so forth. Okay, so in general, is fa plus or minus n fs. All right, so this set of frequency will be able to give you the same kind of a sequence value as x240 and x1000. And this is actually not too difficult to understand, because my original cosine sinusoidal signal after sampling will be 2 pi fa times n ts, right, plus the phase angle. Now, I can replace fa by plus or minus n fs. So it's an integer multiple of the sampling frequency, and then maybe I should use this one as m here, so to differentiate from the other n ts here, right? So when I multiply that, I get n ts plus a phase angle. All right. So I cross multiply, I end up with cosine 2 pi fa nts plus or minus 2 pi m fs times nts plus a theta. Okay. So over here, you can see that the fs times ts is equal to 1. So you end up with 2 pi have the sampling rate is the same kind of sequence. So I cross multiply, I end up with cosine x. My to get the value as x240 and x the 1000, right? And it turns out that if you, yes, there are many other set of sinusoidal signal, as long as the frequencies are f analog plus or minus the sampling frequency, or analog frequency plus or minus 2 times of fs, and so on and so forth. Okay, so in general, is fa plus or minus n fs, right? So this set of frequency will be able to give you the same kind of a sequence value as x240 and x1000. And this is actually not too difficult to understand, because my original cosine sinusoidal signal after sampling will be 2 pi fa times n ts, right? Plus the phase angle. Now, I can replace fa by plus or minus n fs. So it's an integer multiple of the sampling frequency. And then maybe I should use this one as n here. N here, so to differentiate from the other n ts here. Right. So when I multiply that, I get n ts plus the phase angle. All right. So I cross multiply, I end up with cosine 2 pi FA NTS plus or minus two pi NFS times NTS. 2 pi FA NTS kind of sequence values, okay? And These are called the alias frequency. And for this particular case, when this analog signal here with 60 hertz, this is actually 60 hertz. After the sampling at 240 and 1000, so here you are taking 4 samples per period, and for this case you are taking 16.67 samples per period. All right, so you end up with a discrete time signal shown as a blue curve, blue dots here, 1, 2, 3, 4 sample per period. And in this case, you are taking 16.67 sample per period because the period here is actually over this interval of 4.167. Okay, and you can actually recover back this original signal from either sequence, no problem, after going to the digital to analog converter. Now let us take another example, example 3 here, to illustrate this kilo. Okay, let me repeat A and B. So let's chosen properly. So it's discrete time signal after sampling will be, I just replace T by NTS here. So the original signal has a frequency of 213. So it's 2 pi F. T here end up with NT. TS. And my TS is 1 over 1000. So I group 213 over 1000. And this can be simplified to 213 over 500. Okay, because this one will 213 over 1000. This is for the part C case. My sampling frequency now is actually 200 hertz instead of 1000. So we're going to see what happened. In this case, my TS is 1 over 200. Okay, so I'm working through the same problem here by replacing T by NTS, where TS is 1 over F S, which is actually 200. So I end up with 10 cosine 2 pi 213 divided by 200 times n. And this 213 over 200 is actually, we can actually rearrange it as 1 plus 13 over 200. So the idea here is actually that this, you want to rearrange this in such a way that the FA over FS is actually less than 0.5. okay, over, which, so you can see that the original frequency is actually 213, but after the digital to analog converter, what you get back is actually that you get back 13 hertz instead of 213 hertz, 213 hertz. This is actually due to the fact that it is under sampling, and this 13 hertz here is known as the LAS frequency. And to understand that is actually not too difficult, because you see your original frequency FA here is actually 213. So the Nyquist rate is actually 2 times of FA, which is actually 426. And here you are only sampling at 200 hertz, which is actually below the Nyquist sampling rate. Illustrate the importance that hertz, okay, and given by this